Hi everyone, my name is Takahiro Nishimichi from Kyoto Sankyo University. First of all, I'd like to thank all the organizers to having me here. I really enjoy very detailed and very advanced discussion on field level. So there are so many field level talks, and I am going to talk about much simpler stuff related to emulator. But so at the same time, I'm involved in field level with Ken also and Don Hee-jong. And also Palma Group, Massimo Pietroni, and Matteo Peron. So many telecoms on field level. But so I'm not touched about that. So very simple story. Okay, so because the title of this workshop is Theory Meets Numerics, I chose a topic which is really kind of combine theory and simulations. Out of some other topics that I'm right now covering. So one thing that I would like to remind you is that on very large scales, like K.1, 0.12, and so on, EFT is pretty good. So we did this challenge with 2 teams from both coasts in the US, and they returned very consistent results. And so we are very confident. So why not use this theory part as a kind of ingredient in emulator. So that's my thought. And also P plus B is all done by one of the 2 teams and also other teams. And so now kind of saturating, maybe according to Kazu, so because of the degeneracy breaking, maybe we are close to optimal, but I don't know. So I don't touch about the field level potential, but anyway, so I am personally pretty happy about this result. So what to do? So of course we know there are information on small scales, and I don't know if these are really carefully checked, but there are some papers on small scale RSD to put constraints on F sigma 8, right? So there are many data points here, and many from emulator and others from data-driven approach. So information is there in small scales. So how to combine? So that's my topic. Yeah. Okay, so now we are conducting a project called DAC Quest 2 after kind of success of DAC Quest 1 for Subaru HSC, which was used in the 2x2 point analysis, weak ranging, Galaxy ranging and Galaxy auto correlation function. So we would like to extend. And one thing that we are seeking is to extend the parameter range, but in a more efficient manner. So not just increase this rectangle region, but we know that S8 is the main parameter from weak ranging. So we just put the constraint on S8. So we just want to cover this kind of banana shaped region, which I show here, with a bit fatter, like up to 4 or 5 sigmas. So that's a new simulation design. And another thing we added in this second edition of DAC Quest is to explore massive neutron masses and spatial curvature, as well as time-varying dark energy. So that's what's going on right now in Japan. So I just sketch what is new in our new project. So one thing is just implemented a new n-body simulation code called Ginkaku, which is taken from this temple near Kyoto University, Ginkaku. So this is just a 3 PM code. And largely, on large scale, we just follow this Green Ishiyama implementation. On the small scale, we use this framework, FDPS, for kind of very portable library, which is used in any modern multi-CPU or multi-nodes machines. And so this communication between nodes or domain decomposition and so on. So these are all automatically taken care within this FDPS library. And this basically computes 3 force. So we combine Green, PM, and FDPS to get a kind of very scaling result. This is Ginkaku red line. And so now we working on Fugaku supercomputer. So let's check this number. So these are the number of nodes, and one node has 48 CPU cores. So it scales pretty well, up to huge number of CPUs. And also implemented, because we are now interested in massive neutrino, and we know that this affects on only large scale, and small scale is dumped neutrinos do not contribute to the structure formation of small scales. So we use a very simple method based on the, where is it? Okay, for this linear response method. And so also included is clustering dark energy. And so what we do is to run a class or camp with these new parameters, and it automatically takes care of dark energy clustering on large scale. So we just multiply the missing factor in the simulation particles. So simulation particles are only CDM and baryon. So we just additionally multiply the Green's function to approximately include these effects. So as long as these are small correction and on large scales, we believe this is fine. And also, so I forgot to mention, but the tree part is accelerated using, so right now it's not the GPU, but using a library called Phantom Grape. So this is pretty fast, SIMD instruction set, so it's pretty fast. So that's what we are using right now. And also we are very careful, we just test the convergence against, for instance, here we just change the softening parameter, but so this is coherent with time steps. So it's a kind of two-dimensional test, varying both softening lengths and time steps, and to really understand this non-monotonic behavior on large, small scales. And also we compare with other codes. But before that, so now the limiting factor is resolution. So no matter how well we compute the force, so because the initial condition, we do not implement this sheet interpolation or whatever, so we are limited by the Nyquist frequency, which is in the initial condition. So I compare 3 simulations with different number of particles, and basically Nyquist frequency is kind of a limitation. So after that, we also check with existing simulation data. So this is from Euclid comparison, code comparison project by Schneider et al. So we downloaded the initial condition and run using our simulator, Ginkaku, with different settings. And so we basically have 2 options, fiducial, which is tuned to reproduce Gadget 2, which was used in DarkQuest 1. But we understand that this is not perfect. So when we increase the number of steps and also shorten the softening length, we get a bit higher power spectrum on the large K end. And we can basically recover Ramses or PKD graph 3 or whatever, depending on the choice of the parameter. So we are kind of confident how we can proceed given the requirement. Okay. So no baryon, but just matter power. Okay, so just a brief sketch of what's going on. So another thing is that we just, so this is based on Rockstar MPI version, but we just record all the shapes of dark matter halos and subhalos, as well as the hierarchy of them, and at different radii. So as a function of radius, we have shape. So this is for intrinsic alignment. Also, so this is density field as well as gravitational potential field. So this is consistently computed using this 3PM framework. And we are confident that this is kind of converged. So this could be used in gravitational redshift studies. So other things, maybe to me. Okay, so this is same, the potential structure. And also Litecoin is also available. And this is just an advertisement I just took from Adorian paper. So we added two columns here. Now, so this initial stage of Ginkaku Litecoin is done. So this was done in MAOJ, National Astronomical Observatory supercomputer. But now we use Fugaku. So this O or I are person name. So O is Osato. So Ken is now leading this effort to really have many particles to generate many light cones. So this is for weak ranging studies and also cross correlation between different probes like half dome. So the idea is very similar. Okay, so main topic here. So what I would like to address is to control large scales based on perturbation theory. So this is from 3 realizations of 1 GPC cube simulation at redshift around 0.5. And each color shows each one realization. After taking the average over 3 lines of sight, so this is halos in redshift space. So one GPC, maybe if you worked on simulations, you know this is not sufficient. So BAO feature is pretty very scattered from realization to realization. So what we are proposing is to have this very smooth black curve based on some theory and stitch to the direct simulation result, both for monopole and quadrupole. So what's the model? So maybe if you are familiar with perturbation theory, you notice that this is not the Galilean invariant, but I don't care. So on large scale, BAO scale, what's happening is really a random flow of particles, making the initial distance, which is close to BAO scale, to some other scale, making the BAO feature smoother. And this was already reported in many previous studies. Like so, this I took from one by Matsubara. But so when he Gaussian filter the linear density field, he got this green curve, which is already close to the full nonlinear simulation result. So we just borrow this idea. So what's propagator? This is just a response of your final evolved field with respect to the initial matter linear density field. So this is just a functional derivative after the averaging. And in, for Gaussian initial condition, we know that this propagator can be measured by taking this combination. So the idea is that most of the cosmic variance are cancelled from denominator and numerator. So we do not implement fixed and paired simulation, but just standard Gaussian initial condition. But still, we can just make a kind of smoother curve for this propagator. And so just for your information, this is just similar to Gaussian, dumped toward high K. Initially said that this is kind of memory in the initial condition. After particle moves from initial condition, the field starts to forget the initial memory. So we know the typical shape of this function. And once you have this kind of filter function, what you have to do is to multiply twice to the linear power spectrum and apply inverse Fourier transform. Then you get this result very similar to black curve. So how we did it more precisely. So this is very nasty stuff. I do not use anything like a symbolic regression or whatever. I just try many different options. So just thinking. Everything is close to Gaussian. And we have, for instance, in real space, we have a linear bias factor in front of the exponential damping. And also in redshift space, we have Kaiser factor. So we know that a kind of high K, low K behavior. So we explore different kind of parameterization with free coefficients like C0, CR, CD4, and so on. Very nasty, but so we model this propagator in redshift space. So it has a directionality. So line of sight is special. And so we expand this K direction dependent function into multiples. And what we found is that up to basically fourth order, quadrupole order, the result is already recovered when I sum up all these terms to check the two-dimensional full propagator. So, but maybe this red curve is pretty close to zero, but we still have some negative contribution. So if you like, you can include this. But this is basically negligible if you are interested in only monopole and quadrupole or the final power spectral or correlation function. Okay, so I just brought the same thing. Now, along different line of sight directions. And if we stop the multiple expansion up to L equal 2, for instance, you have a mismatch dashed line. But if you include up to the quadrupole order, so basically we recover. And so also this is mu dependence for fixed K. So we are pretty fine. I mean the blue, solid line or dashed line. So this is the way how we just fit the measured propagator from simulated halos in redshift space. Okay, so this is the kind of final result. So because I would like not to introduce any systematic bias, so this is not guaranteed. Yeah, this is just a model on large scale. But the thing is that this damping feature is localized, very, very localized in Fourier, configuration space, unlike in Fourier space. What we do is just stitch at kind of scale where, so this kind of feature is no longer existing. So we just find some place where we just change from this propagator model and just direct simulation. And so here we compare very large scale simulation. And the black curve is without any new technique, just the average over 4 realizations. And red error bars. And the model is black curve, so basically match. So as long as this error bar is fine, we do not see any systematic error. And I continue with quadrupole. And so we have to, so this black curve, just propagator prescription, starts to fail to recover simulation result at some scale. So we just stitch. And so this kind of damping or anti-phased BAO feature is very, very recovered in the black curve. Finally, okay, so what we want to do is to run some simulations to resolve very small scales, like ELGs, emission line galaxies. So it is with Fugaku, it's still a bit difficult to have 4 GPC box size. So our main target is 1 GPC simulation with many particles, or maybe 2 GPC. And so here we compare 2 boxes after this implementation. And if we are careful that, so 1 GPC and 4 GPC simulations have different large-scale modes. 4 GPC has more large-scale modes, which can induce more damping, but still we can recover pretty well this monopole feature and quadrupole feature. Okay, maybe I can stop, but so one thing that we are trying is to use something very similar to control variate stuff. So what we can do is that, so we compare halo auto correlation function, halo CDM baryon cross correlation, and linear theory, so on grid, and CB auto correlation. So same halo mass at the same redshift from 5 different realizations. So you can see that linear theory knows that this blue realization typically has smaller amplitude in every spectra. So we just make use of this fact. And so this blue part goes away after averaging over many realizations. So this is unbiased. This is kind of guaranteed. So anyway, so this is nasty, but on large scales, so this one is propagator. This is simulation direct result with some correction to take account of difference between realization. And on very small scale, so we combine grid-based correlation function measurement and direct pair counting. So on small scale, it's a direct pair counting. So we don't have grid information, but still, this endpoint knows, so this blue realization tends to be a bit smaller than red one and so on. So we just take this factor, which is smoothly connected from grid scale and subgrid scale. So anyway, so this is done only in real space, but we are trying to do the same for redshift space. Okay, then maybe this is final plot. So the final model is this gray solid line, and I compare with some individual realization, like a 1 GPC box with 3 level simulated linear theory and so on. And to show that this is not really biased, we try 100 random realizations. And I just compare the direct average over 100 realizations and after this propagator and control variate stuff. So the sigma, the error bar, diagonal component is significantly suppressed on large separations. And also the difference is consistent with 0, basically. Maybe this part a bit off, but maybe within 1.5 sigma. So we are kind of confident. So with one GPC simulation, we can just have a very smooth red curve like this. So I just plot 100 different curves by red, but they are pretty much same. So I cannot distinguish between them. Anyway, so this is the current status. Okay, so maybe I spoke too much, but this is summary. Thank you very much.